what I'm going to do is go through some of the calculations that are relevant to the determination of equilibrium constant that's found in your lab manual. Now, there are two parts to this lab. In the first part, what you're going to do is you're going to make a series of solutions that force the equilibrium effectively all the way to the right. And you're going to assume that the concentration of thiocyanate, or all the thiocyanate that goes in there, becomes your iron thiocyanate complex. Okay, and then you measure the absorbance of that. And that's what I've done here on the top. Okay, you see this graph, absorbance versus concentration of the iron thiocyanate ion. Now, what information do we need to get from this graph? We need to figure out what is the absorptivity constant. Now, one of the things I want to point out is that with this graph, you need to make sure that you force your line through zero, okay? And you can do that when you set up your trend line. Okay, so you force the trend line through 0, 0, okay? And one of the ways you can tell that is, you see on this, that there's no intercept. Okay, all we're given is y is equal to 10,000x. If I hadn't done that, what I would get is y is equal to 10,000x plus whatever the y-intercept is. Okay, so that's one of the ways you check this out. So the next question is, if that's the case, then what is our absorptivity constant? And the answer is, it's the slope of this line. So in this case, our absorptivity constant is going to be 10,000, okay, which is the slope. But the question is, what are the units on this? Okay, and what I'm going to do is I'm going to say, okay, this is two significant figures, and the way I would determine that is based on the concentrations that I got when I did the calculations there, okay? But what are the units going to be? Well, absorbance is a unitless number, and the concentration of the complex has the units molarity. And so therefore, if absorbance, which is unitless, is equal to the molarity times whatever the value of this absorptivity constant is, then the absorptivity constant has to have the units of reciprocal molar. And it's very important that you keep those units, because that reminds you that the absorptivity, or that the molarity is going to have, or the concentration is going to have units. Okay. So that's really the first part. Now, of course, it's going to take you a lot longer to do this first part than it does for me to describe it. So now in the second part, what you're going to do is you're going to mix much lower concentrations of iron and thiocyanate. Okay, they're both fairly equal to one another, and then use this absorptivity constant to determine the concentration of the complex at equilibrium. Now, the complex is kind of a blood red color, okay, and we're measuring these absorptivities, or the absorbances, at 510 nanometers, because that's where the absorbance is maximum. So if we look down here, here's a hypothetical, and these are totally cooked numbers, so it's going to have nothing absolutely to do with what you actually do in lab, okay, other than the calculations themselves. All right, in this case, we make 20 milliliters of solution total, okay? We mix 2 milliliters of 0.00050 molar iron-free nitrate and 4 milliliters of 0.00004 molar potassium thiocyanate. We add 14 milliliters of water to that, so that adds up to a total of 20 milliliters. We find that once this solution reaches equilibrium and we measure the absorbance measures to be 0.1. Exactly, 0.100, because we can measure absorbance to 3 decimal places with the instruments that we have. So what we need to do is we need to figure out, okay, if we assume all that absorbance is due to the complex itself, what is the concentration of the complex at equilibrium, and therefore what is the equilibrium constant value for this? Okay, so the first things we have to do is say, okay, let's calculate some initial concentrations. All right. Now, initially, there's no iron thiocyanate complex in here, but what is the concentration of iron 3? And also, what is the concentration of the thiocyanate ion, Sc(N-). Okay, so what are we going to do? Well, for the iron 3, what did we do? We took 2 milliliters of the 0.00005 molar solution. Actually, I should say that's 2.00 milliliters. And we diluted it to a total volume of 20 milliliters. So that gives us, if we do the calculations, and let me just double check myself here. That's going to give me 5 times 10 to the negative 5th molar. I'm going to find my pen. There it is. Okay, now what about the thiocyanate? In this case, we took 4 milliliters of 0.0004 molar, and we diluted that to 20 milliliters. So that's going to give us 8 times 10 to the negative 5th molar. Okay, now again, we're going to use 2 sig figs because the molarity of the solution is to 2 sig figs. So it's going to be 8.0 times 10 to the negative 5th molar. Okay, so those are my initial concentrations. Now, what's my initial concentration of the iron thiocyanate complex? There's none in the solution at this point. Of course, as soon as you mix these two things together, some of it's going to start to form until equilibrium is reached, and the solution will appear to get darker. And it does take a little while for this to happen. So let's move on to the next part and actually calculate the equilibrium constant from this. Okay. So the first thing we're going to do, now this is already done for you in your lab manual, so you don't have to worry about this, is we're going to write out the equilibrium. Okay, all these ions are in solution, so I'm going to ignore state symbols. So I have iron 3 in solution. I mix that with thiocyanate in solution, and when the equilibrium is reached, that's going to be in equilibrium with this complex, which has the formula FeSCN 2+. Okay, and now we can also write the K sub C for this. In terms of mass action, that's going to be the concentration of iron 3, excuse me, the concentration of the complex divided by the concentration of iron 3 times the concentration of thiocyanate ion. Okay, now I'm going to set up my ice table. All right, initially, what do I have? I have 5.0 times 10 to the negative 5th molar iron 3, and I have 8.0 times 10 to the negative 5th molar thiocyanate. Now, what is the initial concentration of this? We said it was 0. Okay, now, how do we get the equilibrium concentration? The equilibrium concentration is based on our absorbance and our absorptivity. Okay, so at equilibrium, the concentration of the complex is going to be equal to the absorbance, which was 0.1, and again you can go back and look at this, divided by the absorptivity, which is 1.0 times 10 to the negative 4th reciprocal molar. Okay, so if you divide those two out, that's going to give me an equilibrium concentration of this complex as being 1.0 times 10 to the negative 5th molar. Okay, that's a very tidy number, obviously. So what's happened? The concentration of the complex has increased by 1.0 times 10 to the negative 5th molar. Okay, now if the concentration of the product increases, then the concentrations of both of the reactants have to decrease. Okay, I can't have one decreasing and the other one increasing. That's impossible. Okay, so that, and since this is a 1-to-1-to-1 reaction, they're both going to go down by the same amount, which is 1.0 times 10 to the negative 5th molar. All right, so that means at equilibrium, the concentration of iron 3 is going to be 4.0 times 10 to the negative fifth molar. And the concentration of the thiocyanate is going to be 7.0 times 10 to the negative fifth molar. All right, so we have equilibrium concentrations of all three ions, and therefore we can just plug them into the equilibrium constant expression. Okay, we have 1.0 times 10 to the negative fifth molar complex. We're going to divide that by 4 times 10 to the negative fifth molar for the iron. 3, and by 7 times 10 to the negative fifth molar for the thiocyanate. And that'll give us our equilibrium constant. If I do all that, I get 3,571. Now, how many significant figures should I have? It's going to be 2. So the answer I'm going to record is going to be 3.6 times 10 to the third, or 3,600. All right, it's probably better to record it in scientific notation because that eliminates any ambiguity as far as significant figures are concerned. So there you have it. Those are the calculations for this lab. Go over them. Also, I would recommend that you go over making a graph in Excel so that you're ready to do that as well when you come to lab.